Good morning. This is a webinar about optimization and control of challenging distillation columns. The speaker today is Juan Carlos. He has 12 plus years of experience in doing controls, simulation, optimization, and all the various industries that we talked about. Before he jumps into the topic, I'm going to pose a poll. So please take a minute to answer to this poll. This is asking you about which controls have you struggled with your on your columns. So if you would like to share what it is, so it would give us a good view of what you're going to see in the later half of the. Yeah, take a minute to answer this poll, please. While everybody is talking about this, JC has executed these projects across the globe. So he has a good experience in tackling all of these related to these ones. So here is the poll that is out there. So I'm going to post the results, publish the results. Not very surprising, as you can see. These are composition seems to be the hardest one, and then as you can see, pressure and temperature comes later. With this, I will hide this list and hide the results, and so that everybody can listen to what JC has to offer. JC, please take it out.
Thank you, Ravi. Well, good morning, good afternoon, everyone. I'm pleased to be able to talk to you. Let's just talk to you about our experiences with different kinds of distillation columns we have worked with over the years. There's many other examples. These are the ones that we have found relevant for this particular topic because each one of them involves a different aspect of what the process, of what the process is about. It involves a different challenge. So that's why we thought we could start with this one. And then in a later stage and on the second part of the webinar, of this webinar series, what we are going to do is we are going to talk about how have we optimized these columns. So we will go back to some of these examples, or we will have some other examples in which we show you for complex distillation columns, what have we done, what are those solutions that we have found. The scope right now, as was mentioned, is on base layer controls, DCS controls, PAD control, however you want to call it. I think you all know what are we talking about. Three main topics, or three main examples we will touch on. The first one is the pressure control for a heat pump driven C3 splitter column. I think some of you may be familiar with this kind of column. C3 splitters are usually not the easiest column to deal with. I mean, in theory, they seem like they're easy because it's just two components, but very close boiling points, and okay, we have this the heat pump problem as well. And then methanol water, again, doesn't seem too complicated, but devil's in the details. This is a very high purity column. And then the cut point for the cut point temperature control on an extractive distillation column, that's the third example here. I think the main challenge you will see is more related to the fact that you have different liquid phases inside the column. So then what seems to be obvious or almost intuitive for any other type of columns, when you have two liquid phases, well, sometimes just stops being the case. So let's move on to the first example, pressure control for a heat pump driven C3 splitter column. So challenges, as I mentioned before, narrow boiling point difference between propane and propylene, high pressure of operation. These columns operate at at high pressures. That one in particular that we're talking about, I cannot name specifically where was it, but it was a column that was operating around 18 bar. So it's, I mean, you could call it high pressure. High vapor and liquid traffic, that's a given for a citrus splitter. We have a narrow boiling point mixture. You need a very large vapor and liquid traffic. You need to have a lot of interaction between vapor and liquid to be able to do your separation. And you have a lot of trays, huge reflux ratios, so that makes the whole traffic a problem in itself. High purity column in this case, well, it's the propylene in the top is it has requirements of purity, of course. Energy requirements, that can also be the case for citrus splitters. In this case, well, the heat pump is there in particular just to help with the high energy requirements that are associated with such a separation. A flat temperature profile, again, the narrow boiling point difference makes the temperatures across the column basically not change significantly, and a low relative volatility. So what are the common control strategies for a citrus, not citrus splitter, for a distillation column? So typically when you control your pressure, you can have it floating, or you can have a hot bypass or a flooded condenser, or if it's a partial condenser, then you have some venting. For the top level, you can control the level with your reflux or with the distillate, depending on how you manage it. The top impurities you can control with a reflux ratio, or with a distillate to feed ratio, or with internal reflux. The bottom impurities you can control with your boil-up ratio, or the bottom flow. There are many opportunities here. The bottom level you can control with the bottoms product. Sometimes the bottoms level, the amount of material coming out from the bottom of the column is so small that you cannot even control a flow coming out of the column, and you need to control the level just based on the amount of heat that you put in the column. So that's how you control the level in that case. So this is just to show the typical common control strategies, but all this changes when you have a heat pump. When you have a heat pump, well, first of all, what you're trying to do is you're trying to use the heat of vaporization, the latent heat of the mixtures that you're separating, as the source of heat for the column itself. So the strategy, for those who are not familiar with a heat pump, is to take the vapors from the overhead, as is shown here. You take the vapors from the overhead, and then you compress them. So then when you compress them, the temperature increases, and then you can use those you can use those vapors from the overhead of the column to give heat to the column itself. So you are upgrading, basically that will be the word, you're upgrading the heat by means of a compressor. You could not do that if you don't compress it, because the temperature in the top is usually lower than the temperature in the bottom. So there would not be any heat exchange in that case. But because you're compressing it, then the vapors would have a higher temperature, and therefore will be able to give out the heat that they contain. And because they contain, as I said, latent heat, and that latent heat can be used in the reboiler itself to give the heat that the column needs for the separation. So as I said, this is very typical for citrus splitters. The main reason for that being the huge reflux ratio that you have there. If you would need to operate such a column and not do this, then the amount of steam or any other heating source would be huge. That's the reason why you need to do that. So this imposes a challenge. And this is why. So when you look into the citrus splitter itself, so this is the schematic of just one citrus splitter. Not every single citrus splitter is the same. This is just one example of many. You have here that, as I mentioned before, the overhead vapors are compressed in this compressor, and then once they are compressed, they are used in the reboiler of the column. But the reboiler of the column is at the same time the condenser of the overhead vapors. So the overhead vapors condense in the reboiler. Sounds a bit strange, but it's exactly what happens. And then they go to the overhead drum. This particular case is one in which the reflux ratio is close to 20. Why am I mentioning this? It means that the reflux flow is roughly 20 times as big as the top product flow rate. So if you want to control the level in the top of the column, you have no other option but to use the reflux. If you try and use your top product flow as your manipulated variable for your level, well, you would really struggle, because then it would be like trying to control the level of a pool with a little hose. So what happens here is that since the heat generated, or the heat transfer in the top is also the same one as the one used to as for a boiler, then all these vapors condense, and most of those vapors will have to go back to the column again as reflux. So that creates a direct interaction. When trying to control the pressure of this column, so when we first went into this site, what we found was that they tried to control the pressure of this column using the inlet guided vanes of this compressor. This was just a centrifugal compressor, and they were trying to use the inlet guide vanes of the compressor. What is the problem with that? So I won't anticipate. So first of all, let's just remember very quickly what compressor performance curves of a centrifugal compressor look like. So this is how they look like. This is the flow, and this is the pressure ratio. I think we all have seen this kind of curves. And then what we see here is the percentage opening of the inlet guide vanes. You can see that as the guide vanes open, both the flow and the pressure increase. So this is what gives the whole concept a problem. Why? If we just try and estimate, as I write here, like the rate of change at which the pressure changes. Well, the rate of change at which the pressure changes is basically the amount of vapors coming in plus the reflux that is being sent back to the column minus the compressed flow. The thing is, both the compressed flow of vapors and the reflux both depend on the inlet guide vanes position. Why? Let me go back. The guide vanes positions, as you say, they change the mass flow compressed and the pressure. And if you remember, most of the mass flow that has been compressed, it's condensed and then on level control sent back to the column. So the more you compress, the more you open the guided vanes, the more reflux you generate. So it becomes like almost a positive feedback loop. Through this, although this control scheme was implemented there, it was always in manual. They never managed to make it work. It has slow dynamics, and on top of that, it has an inverse response. And I think it's obvious why the inverse response is shown here. It's just the fact that the moment you open your guide vanes, yes, okay, your pulling more vapors. So the first effect is for the pressure to go down a little bit, but then very soon after, those additional vapors will be condensed and sent back as reflux. So it just became a problem. So what did we do? We just analyzed the process and said, okay, there needs to be a way of decoupling these. So this is what I was describing previously. As you open the guided veins, both the mass and the flow, as the mass flow and the pressure increase. So how can you decouple that? So you can see here that there was a part of this schematic that was not shown in the previous slide, but you can see it in the process schematic. Let's quickly go back. You can see here, I don't know if any of you noticed that part of the vapors actually go through a separate condenser. So not all of the vapors can be condensed in the reboiler. A part of them are actually condensed in a little condenser that uses cooling water. So if what you do in this case is using the valve that controls the amount of flow that goes through that condenser, the one that uses cooling water, then you can improve your situation, because what happens in that case is that the reflux itself depends on the guided veins, because it depends on the amount of vapors that you compress. But the amount of condensate depends not only on the amount of on the guided veins, but also depends on how much of these vapors are you sending to the cooling water condenser. So this decouples the whole problem, and because of that, then what happens is that you don't have to move anymore your guided veins. You can leave them at whatever position you need. So you're not basically producing more reflux. The reflux, let's say, stays constant, and then what you can change is the velocity at which you condense, and you can do that just by changing how much of it is going through the cooling water condenser. So that's exactly the strategy we proposed. Once you see it like this, it sounds like a simple thing, but trust me, it was there like this for many years. So it sounds simple enough. The pressure should actually act on the valve that controls the amount of vapors that go through this little cooling water condenser. And once you do that, the effect was very clear. You can see that before they tried to do some control, but they never succeeded. But after we implemented that PID control, pressure was very tightly controlled at the set point. One other interesting thing is, and probably you were wondering, why did I write this equation as a differential equation? Well, at the end, the pressure in the top of a column is like an integrator, so it behaves in that way. Its behavior is more related to the rate of change than to anything else. And that's what this is showing us as well. You can see that whenever you make a set point change in the pressure, the output of the controller first quickly jumps up and then comes back down to pretty much the same place where it was before. It is the case. The guided veins are at the same position, so the amount of vapors that you're compressing are exactly the same. You're not changing that. But what you're doing is very quickly trying to condense them faster, so then your pressure decreases, and then once you manage to make your pressure decrease, then you go back to the original point, because the amount of vapors didn't change, so you need to still condense the same amount. Okay, so next example is some methanol and water column. This column is also a very big column, more than 100 trays. The top 30 something trays do not show a single decimal of a degree of change in temperature. because in this column, you're looking for methanol, which has a purity of 99.999% or something. Basically, the impurities are measured in the ppm region, and the ppm, we're talking about something like 10 ppm, 5 ppm region. It needs to be really high purity methanol that you produce with this column. That's what this company sells, and of course, they need to meet that standard. Ultra high purity product, high energy requirements because of the same thing is the same problem. At the end, if you need to cut very deep, the more you need to cut, the more you need to separate, the more energy you need. And in this case, it's a very high purity cut product. Flat temperature profile, as I mentioned, the first 30-something trace of the column just don't show any change in temperature because it's mostly methanol. Probably 30 traces below the top, you have 99.1% methanol, and then in the top, you have 99.99. You do the math and tell me how much can the temperature change in such a small composition range. But is what they sell, is what they need to get. And on top of that, this methanol is produced with syngas. So the conversion is not perfect to methanol. There are some impurities, mostly ethanol and some higher alcohols that you need to get rid of. So you have a mid-cut impurities. This is a schematic of the column. You feed your mixture of methanol, water, and some other hydrocarbons, as I said, mostly ethanol and propanol and stuff like that. And you need to separate it. So what did we find? What did we find? We found this. We found a column in which there was no real control of the bottom duty of the duty to the column. This is low pressure steam that is used in this reboiler. It was just there was just no real control of that. It was more like as you can see, a demand type of system, depending on how much liquid was coming here just to keep a level, then it was boiling more or boiling less. But there was no real control of that. As well, for the side product flow was associated to some temperature controller in a downstream column, which was not really that sensitive to the amount of impurities. So it was not easy to control. And then what we found there was that there were throughput instabilities because of the kind of control that it was using. You can see how this cut temperature, the mid-section cut temperature, was controlled with the feed flow. And this is not to say that that was a wrong strategy. This is to say that the way it was implemented was not correct. Big duty variations, exactly because of what I just mentioned. Very poor pressure regulation, poorly tuned top level. So what did we do here? Here, well, the first thing was this. Instead of controlling the side stream flow with a temperature controller, the side stream flow was configured as a ratio controller with the feed. Basically, saying that if the feed changes, if the feed goes up or down, then so does the side flow, and that helped enormously to keep the specification in the column, because it meant that you were always trying to extract the amount that you needed. Of course, that ratio can be changed in case you need a little bit more of drop product, of side drop product, just because you're seeing that your impurities are increasing somewhere. But this is much better than the previous strategy. The previous strategy was based on measuring after and then acting. This ratio strategy gives you a lot more anticipation to what can happen. So it has proven to work, and it has worked there for many years, over 10 years. It's just okay. Second problem we found, as you saw before, there was a temperature controller for the sensitive tray in this middle section that was attached to the feed stream to the column. As I said, that was not per se a problem. It was how it was implemented. The pressure in this column is controlled with fin fan coolers, and this was in a very hot place in the world. I'm not going to mention exactly which country, but it's very hot. It reaches 50 degrees sometimes. You probably know where it is. And of course, summertime, even if they have these fin fan coolers maxed out, and they try and wash them as often as possible, still they need to operate at the maximum, and still the pressure cannot be maintained all the time. So the pressure fluctuates. I mean, it's within an acceptable range, but the pressure fluctuates during the day. So especially at midday, the afternoon, the pressure increases significantly, and then at night it reduces a little bit. What happens with that? The problem is that if you have a floating pressure in your column, then the temperatures themselves are not anymore a representation of the composition. So what do you need to do? In that case, what you need to do, you need to find a pressure compensation for your temperature measurement. And that's exactly what was done. Because the mixture that is being separated here is, let's say, somehow an easy mixture to find literature about. So it was possible to find enough literature to calculate this pressure compensated temperature, and it just matches very well the real behavior. So instead of controlling this temperature raw, it is now pressure compensated, and that pressure compensated temperature is the one that is now being controlled with the feed flow of the column. So this already has helped a lot in keeping the separation around that section a lot more stable. And then lastly, as I mentioned before, for the bottom part of the column, there was no real duty control. So this is what we did. We implemented a duty control. So that duty control basically acts on that original level control that was implemented there, has some feed forward effect using the temperature, the bottom temperature of the column. But the important thing here is now you have a constant duty. So the fact that you have a constant duty already gives you a lot of stability. In fact, it is with the duty, at least before we did some other, before we implemented advanced process control here, just on the regulatory control, this allowed them to have a more clear handle on how to change the production. Before, if you remember, the feed flow was attached to that temperature controller, so it was not that clear for them how to change production, how to increase or decrease production. But here, this gives you the handle that you need. So if you can change the amount of steam that goes through the reboiler, then you're changing basically everything in the column. So if you increase the amount of steam, for example, then obviously that this temperature, this sensitive temperature will try to increase. And then to compensate that, the column will bring more feed in. So this is indirectly the way they were controlling the feed of the column, and that worked very well. So this strategy, as mentioned before, helped to do many things. One of them, to have a tighter overhead drum level control. Just the fact that your reboiler is now more stable already makes your vapors more stable, and that together with good tuning made the level control better. The pressure compensated temperature of the draw tray, that was also a really good improvement. Feed forward action on the bottom level, also a good help. and then some pitch control on the fin transfer pressure regulation. So you can see here how the reflux of the column used to vary a lot before, and then after we did this, it really changed. Bear in mind that this reflux is attached to a reflux ratio controller. So even with the reflux ratio controller, the reflux was a lot more stable. As mentioned before, yeah, the methanol, the reflux ratio is also more stable. It was moving a lot less after the whole implementation. The top level of the column was just, a mess. It was oscillating all the time. After the changes were done, it worked a lot better. And this is one of the most important improvements, the side cut temperature, the one that we have been talking about, the one that has the pressure compensation. Well, it was basically the sum of all the changes, of all the improvements. You can see how the side cut temperature changed from a huge variation, huge variability, to a very tight control. This very tight control really allowed the product to get to specification with a lot more consistency, and also it stabilized the whole system. Because if you see a temperature like this, like it was before, changing so much, and if you remember, this temperature was controlled with the feed flow, well, you can imagine that if the temperature was changing like this, the feed flow was doing the same. But after this improvement was done, so it was definitely a big change. All right, so third and last example. This is a bit quick just to be able to show these three examples. Is the cut point temperature in a control, cut point temperature control in an extractive distillation column. The process, this is an extractive distillation column using N-methyl pyrrolidone as a solvent. That this will involve different liquid phases to separate non-aromatics from a benzene product. The top distillate is basically the non-aromatics with some little benzene that, let's say, is entrained to the top. Let's say entrained, and now you will see why entrained. The bottoms would be the solvent with the extracted benzene. Then after that, the solvent and the benzene will be separated in a stripper column, and the stripped solvent, which is recycled back. Steam will be used in the reboiler. So this is a little schematic of the process. This is basically what we explained, the extractive distillation. You have your solvent coming on the top, and steam at the bottom, basically extracting the benzene from the non-aromatics. So you can imagine that at some point here, you will have different liquid phases. The non-aromatics and the benzene will no longer belong to the same liquid phase, and that will make things very different. How different, would you ask? Well, this was the initial control structure, and to be fair, we cannot blame them. It sounds like logical. If you think of the solvent as almost like a reflux flow, well, it's only logical to think that if you change your solvent flow, your top temperature, your top temperature, or your sensitive temperature in the top of the column will change accordingly. So that's exactly how it was implemented. You can see here, it was a temperature controller that was acting on the amount of solvent. I mean, it's not as simple as that. You can also see there's a feed to solvent ratio that is kept, but basically the temperature controller was acting on the ratio to change the amount of solvent. That's exactly what it was doing. Let's say on a fixed feed, for all intents and purposes, this temperature controller was trying to act on the solvent to change the temperature, again, as if it was a normal reflux column. But remember, this is not a reflux. This is an extractive distillation. The purpose or the whole function of the solvent is not only to, yes, of course, cool down a bit and condense, but is more to do the extraction from the other liquid phase. So chances for this to actually change the temperature in the top are slight, because the temperature in the top, as we mentioned before, is mostly non-aromatics. And the solvent is a solvent for benzene, not for the non-aromatics. So it means that effectively, if you change the amount of solvent, the composition of aromatics on a benzene-free basis does not change that much. So that's why the temperature was not being able to they were not able to control it as they intended to. So that tray, the 49 temperature, the temperature in the top of the column, is a very good indication of the amount of benzene that slips to the top. So a good control of that temperature is important for the column, because, as I mentioned before, there is a maximum amount of benzene that is allowed in the top non-aromatic product. But with the implementation that you saw, it was a bad and sluggish control. So this is an example. This is the control in automatic. You can see there was basically no control. The ratio of solvent to feed was changing big amounts and seeing basically no effect at all on the top temperature, on the sensitive temperature. It was just not working, basically. Now, and the reason why is what I just explained. What did we find? We found first that, as we mentioned before, the temperature in that tray correlates very well with the amount of benzene that slips in the top, so you need to control it properly. And we also found that, in fact, it is the steam in the bottom what really changes the temperature in the top. And you say, okay, yeah, well, that sounds a bit obvious. And you would argue, yes. But the thing is, you have 49 trays from your bottom to your top, at least from the tray to the tray where you measure it. So normal control design considerations will tell you, oh, you probably need to find something closer to try and control it. And I would argue, and I would say, yes, that's usually the case. But in this particular scenario, that was not the case, because in this particular scenario, to change the amount of benzene that goes to the top, that escapes from the top, you can only change that from the bottom, because the benzene is actually coming out from the bottom. So of course, if you increase the amount of steam, then more benzene will rise up and increase the amount of impurities in the top. The challenge here was that obviously the control here is not as fast as you would want it to, because again, you have 49 trays until you see the effect, but it doesn't mean that it cannot work. With proper tuning, it can work, and this is what we found. We were able to set up that temperature controller. That temperature control made it easier to keep a much tighter benzene giveaway. Now the ratio between solvent and benzene in the feed can just be set by the operator. So they also have that handle if they need to use it for some specific reasons. And the bottom temperature is just not controlled. It's not a quality indicator. The best quality indicator of the separation here is that temperature in the top. And you can see here how, in this scenario, in fact, you see it responding. It is slow, yes, but it does respond. You see that once you make a set point change, the steam changes, and then initially you have some dead time, but then at the end you get your response. Obviously, tuning a PID loop with a dead time is not easy, and depending on how long the dead time is, it can actually become impossible. But in this case, dead time was not that long that you could not somehow find a set of PID parameters that allow you to do the control. And it was working, and it is working to the point that on top of that, we were also able to put an advanced process control solution, and it helped optimizing the plant. Okay, so benefits achieved: tighter cut control, better control of benzene in the top, easier for operation to optimize, and it was APC ready. But I mentioned that we actually put APC after that. So as general guidelines of when you're dealing with these distillations that are not as intuitive and typical as you usually find, there are some principles that will never fail. Heat, material, hydraulic balance should always be reinforced with base layer strategies, always. I think we found examples of each one of those in the previous slides. Proper PID tuning, I mean, I think we all know that, can bring process back to stability. You need to understand your process, you need to understand your dynamics, and do proper PID tuning. Composition control is advisable where possible. And I know that was one of the questions that you asked. Is it possible? Yes, it can be possible through many means. It could be either because you control a pressure compensated temperature that is very closely correlated to the composition itself. Maybe if you have a reliable enough analyzer, you can implement a control with the analyzer. Of course, you need to be careful. If the analyzer is measuring every 10 minutes, well, maybe you need to think about it again. But I mean, where possible, it is advisable. And then, just as we mentioned in the previous example, the manipulated variable for the base layer strategies can be chosen based on both proximity, which is the initial instinct, but also based on sensitivity, if conditions allow you to. All right, I think I managed to do it on time. That's it. Thank you.
Hey, thanks, JC. That was a very good presentation. Please use the Q&A section to ask any questions. We'll try to answer as much as possible in this session. So I have one question here already. What is the difference between reflux flow control based on a specific tray temperature and the temperature difference between two specific trays?
Okay, well, I'm understanding that this reflux flow control is cascaded to perhaps the sensitive tray in the top of the column. That's my guess. So based on my assumption, please indicate if this is exactly the case. If my assumption is correct, well, the difference is that, yeah, if it's a specific tray, then you're affecting the composition in that specific tray. That's what you're looking for. You're not really looking at the rest of the column. So the effect should be very clear. Whereas if you change the reflux based on the temperature difference of two specific trays, then what you're doing is something different. What you're doing is just changing the slope of the curve, of the distillation curve, your operation line. If you all remember, the old distillation theory, the McCabe-Thiele diagrams, then you have your distillation curves and your operation lines. You're changing the slope of your operation line. So basically, you're changing the amount of separation without actually looking for a specific composition. That's what happens with the different when you use the difference between two specific trays. But if you try and control a specific tray, then you're aiming for a specific composition. I hope that answered the question.
Hey, Thanks, JC. Please ask any follow-up questions if you have any on that topic. But here is one more. Do I need different control scheme for different loads on my unit?
Well, if we're talking about distillation columns,
yeah,
then I suppose then the best answer should be how flexible is your distillation column. Every distillation column has a turn down rate and a maximum rate. So if you have some additional geometry inside the column that changes when you need to increase or decrease your production rate, then yes, you may need to change your control strategy. One other thing that I could say about this is sometimes if the column is flexible enough, what can happen is that you have, for specific controls, you have different valves. You have a small valve and a big valve. And then when you're at low rates, you use the small valve, and when you're at high rates, you use the small and the big valve. So yeah, that's also something that somehow changes the way you configure your base layer.
All right, here's one more question. Can I directly use analyzers to control my product impurities?
This is what I mentioned before. Is the analyzer fast enough, reliable enough? If the answer to both questions is yes, then I would say yes, you could. There would be no issues. The thing is, remember, PID controls run every second, half a second, whatever. And if you have an analyzer that is giving you a new signal every 5 minutes, well, you need to start thinking about it. If you have big dead times, because sometimes analyzers have transport lag times or whatever it is, those dead times also make it very complicated to try and configure such a control. Or if the analyzer is just per se, the technology of the analyzer is not that reliable, then that is also something that you need to think about. If you know that your analyzer tends to drift with time, there you go. If your analyzer needs to be maintained very often, same thing. So the answer to the question is not a single one. It's just, it depends on the situation. But again, if you have an analyzer that is fast enough and reliable enough, I would say yes, you can do that. I mean, you have examples. It's not exactly distillation, but in furnaces, you can control excess oxygen. Why can you control excess oxygen in furnaces? Because it's such a simple and reliable technology that analyzers are very reliable and very fast. They really give you like an instantaneous measurement all the time. If you can get something like that for your particular distillation column, then yes.
Yeah, there's a question about how about using MPC on distillation columns? Answer to this is please attend the next series on this topic. Is exactly what we will be talking on.
Yes.
At applying MPC to solve some of these problems. Not all problems can be solved by MPC, as we discussed today. Some of them can be done base layer only, and some of them you need MPC. Some of them you may need totally different things. So
yes. We have some examples in which it's actually MPC what really helps you getting a better control.
Yep. So there's a question on while still in design stage, how best these controls related challenges be addressed, especially if you're not sure how they behave under different site conditions. It's a very challenging question, but I guess
please
go ahead.
Yeah, no, it's true, Ravi. It's a challenging question. So what can I tell you? When still in design stage, I think you can still do many things on a design stage. First of all, you can run a sensitivity analysis of your column. You can check for your different handles around the column and check the sensitivity of your key variables to those. And that you can typically do with steady state simulations. Whichever tool you use, steady state simulation should help you get that initial feeling of how sensitive different variables are. Also, with steady state simulations, you can in fact get to understand interactions between those controls. Even without implementing them, you can run this typical RGA analysis, relative gain analysis, that will really help you understanding if the strategy that you're thinking of is, first of all, feasible because there's enough sensitivity, and second of all, let's say realizable because the interactions between the loops are not that strong that at some point will just not allow you to have such a control. A very silly example is on a design stage, using this kind of simulation, you can easily know if you can put or not two temperature controllers in the same distillation column, which is typically said, oh, you should not do that. Maybe in your particular case, you can. Maybe. It depends. I mean, there are many kinds of distillation columns, so there's not a single answer. Now, so just to finalize, and then once you've done that, the rest of the challenges, which are more like the dynamic challenges, well, those can be evaluated with a dynamic simulation. If you have enough resources to do a dynamic simulation of your column, for sure that will also help you understand many things about sizing valves and and stabilization times and stuff like that. Okay. Yeah.
Yeah, there are a few more questions. Some of that could be answered with my poll, next poll. One of the question is, when would you like to have this next, when are we scheduling our next one? So instead of me answering that, I'm going to start a poll, see how many of you are interested in the next one. Please answer yes or no here. Really appreciate that. So far, I got a good response here.
Yes, I see one that's there's a question I see here that looks like it's answered, but it hasn't. Is if pressure floats, does tray where temperature indicates composition shift? I don't think I have answered it.
Yeah, I think he found the answer in your slides already. So
that's okay. Yeah. All right.
Yeah. So, okay. So here is the results. Obviously, quite a few of them, 96% of you have said yes, you would like to see the next level. So that will be there. So if with that, I'm going to poll one more. When would you like to see? Which month? July, August, September? Please, please give your preference, and we'll try to meet as many as you possible. In the meantime, please ask your questions. If we can't answer all the questions in the time we have probably only 5 more minutes. We will answer them by email. I
think I can answer the three questions like I see here.
Yeah.
Sorry, two. Yeah. So what is the difference between using a PCT in the base layer and a PCT in APC? That's a very interesting question. The difference is that, well, with APC, you're controlling the multivariable approach. So with APC, the handle that you're using to control your PCT may not always be used to control your PCT, because there may be some other constraint in the plant that the APC needs to react to. So it will not be a continuous control of your PCT. If you have a PCT in the base layer, then that PCT control will be done exclusively by that handle that you're choosing, whichever it is. So it means that it will not look at any other constraints. Is that what you want? Maybe that's what you want. Maybe that's what you need. That's what we found, for example, in the exam in one of the plants in which we implemented the PCT. The example for the methanol column, that was exactly the case. We decided to do it in the base layer because we knew that was exactly the handle that we needed to use for it. and there was no need to use it for anything else. So that's I would say the main difference between the two. In terms of response, I mean, you could argue a PCT in the base layer could respond faster because it's a PAD control. But that being said, given the typical dynamics of a distillation column, maybe it doesn't make much of a difference. Anything using soft sensors? That's another question. Yes, that basically is something we will talk about in the next webinar. How to use those soft sensors specifically for advanced process control. But yeah, I mean, in the cases when your analyzer is not reliable enough, for example, maybe your composition control can be done instead of using an analyzer only. You can use some soft sensors. So you can use that. Sure. But again, we will go into a bit more detail about soft sensors in the next seminar.
Yeah, one last question, maybe.
Yeah, there's the last one is there are a number of ways the control pressure can be controlled. However, there is no straight answer to choose one strategy over other. Can I show you some light? Yes, I can show you some light. With the light is, let's understand the process first. First and foremost, it's exactly what I showed in the first example. I mean, who would tell you just from the book that what you needed in the first example in the C3 splitter was to go and act on the amount of vapors that were going to the little, almost forgotten cooling water condenser? I mean, unless you do a process analysis, you really understand the process and understand the interactions, then you get to know how to choose a strategy. I mean, there's not a straight answer. Yes, of course, there is not a straight answer. But the best answer I can give is that process comes first, understand the process first, and then the rest typically just comes.
In the interest of time, that would be the last question. So just wanted to thank you for everybody for attending this one. We just released our new website. Please go to IPCOS.com. You will see a lot of use cases related or maybe a little different from what you have seen today that are published there. So you can download them and ask any questions. So you can email us at the email that's shown on the slide. And the other thing I would like to say is we will announce our next webinar as soon as we gather ourselves, and watch out for that. And lastly, if you need access to the webinar, we will be posting that on the website too. You can watch this video and share it with your colleagues, those who could not join today. Thank you again for attending this one patiently, and really appreciate your time today. Thank you.